All right, everybody. Thanks for joining another EERI seminar. Today we've got Mustafa, who needs no introduction, but I will anyways. So he's currently working on his PhD here at UNR, but he got his Bachelor's of Science from Shahid Beheshti University in Tehran and his Master's in Science of Geotechnical Engineering at Sharif University of Technology. So far, a lot of his research has been about numerical and experimental investigations of soil structure interactions, specifically focusing on seismic analysis and the design of buried bridges like we'll hear today. So with that, take it away.
Thank you, Noah. Thank you everyone for joining today's meeting. As Noah said, we are going to discuss something about developing seismic design criteria for buried reinforced concrete arch bridges in both sides, both numerical and experimental. And we'll see how they work. But before the end, let's see. It doesn't work. Oh. Let's see what we're going to go through. We're going to talk about the motivation of research, the numerical modeling overview, so we kindly do it. The simulation result, we give some experimental program and the preliminary finding that we have done so far, conclusion and future work references, and at the end would be question and answer. I hope that could go all well. Let's start. Whenever we talk about damages in earthquakes, we normally see about structures on surface with huge piles of, let's say, damages and everything. But the structures which are buried and under the soil are commonly kind of immune, and they do not get as damaged as the surface structures. And that comes from the intrinsic behavior, the difference between the surface structures and buried structures, which is, for example, when we have surface structures, it's stayed on top of footings, and the only way that the load gets transferred to the structure would be moving the ground. The structure would have inertia. Inertia will, for the first time, resist from the movement, and after that, it will move. And those residual movement, are the things that apply the seismic demands. But for the buried structures, it's a little different. The whole thing would be buried in the soil. The whole height of the structure will be undergo the seismic deformations and everything. It can cause some complexity and everything. For example, here on the left-hand side top figure, we can see the picture of the very recent earthquake in Myanmar. But this earthquake was this building was in Thailand, which was one of the consequences of that earthquake. We see that the skyscraper just goes down. Figure B is the Loma Prieta, and it's California in 1989 that we see that all the structures on the surface are getting damaged. But the things happening underneath the soil are interesting. They are not very common. But still they can happen. That you can see, for example, in Kobe earthquake 1995, the Dakai subway station has been through a tremendous damage that we can see. Because of all these things, the design codes do not consider specific seismic design codes for the buried structures, and they say, okay, that they are immune, and we don't need it. But in contrast, some damages will happen, and we need to take care of it, especially for the very long span bridges that we will going to cover. What is my project? Probably all of you have seen these type of structures. We are calling them buried arch bridges, which are crossing highways. They have live loads on top of them, and also the traffic goes below. They have been constructed over 30 or 40 years now, and they have a lot of advantages. For example, because they can be built prefabricated concrete, they are super fast in construction, the low maintenance cost. Their performance under both live load and dead load of vehicle and everything is so robust. The material saving is a good thing about that. They can be built in both corrugated steel and reinforced concrete, and also they can come in different geometries, different lengths and spans and rises. But one of the major problems that they have is the thing that I told you. In design codes like AASHTO, they are not specific design codes, seismic design guidelines in order to create these ones or construct these ones. And they are only designed based on, let's say, only the dead load and live load, the thing that are traditionally exist in the design codes. And our research objective here is to develop a validated numerical framework for seismic analysis of buried these type of structures We're going to investigate the SSI effect on, which is soil structure interaction effect on seismic response, and also deformation patterns. And basically we see how they deform and how they damage probably. And at the end, we are going to evaluate the limitation of existing design codes for buried structures and proposing performance-based seismic design criteria or some updates to the existing ones. By being said that, let's see what we are doing. My job is being done in ANSYS LS-DYNA, which is a general purpose finite element simulation tool that can be used for different aspects, for different purposes. For this case, we are using this SSI analysis in this software. And here we can take a look at my 3D finite element model that I have generated. As you can see here on the left side, we are seeing my whole domain, the soil and the structure in it, that we can zoom up later on and see how this looks. But first of all, let's take a look at the boundaries. At the base, we are seeing that I'm trying to fix my boundaries. And I try to apply something to the side of my soil domain called periodic boundary condition. This is done because I'm going to make sure that my soil domain is large enough so no significant wave reflection comes back to the domain, and that happens that can be actually mimicking the real world. Because in real world, we have far field waves goes on, but in numerical analysis, we need to make sure of these things. We can do it either by using periodic boundary condition and make the soil domain pretty long, or we can put some dashboards and these things. But the main concern in this in my simulation is that I'm using fully nonlinear material in my concrete, soil, steel. And because of that, using those dashboards are kind of not very, let's say, we can say a certain way in order to do that. So we go with a little more simplified method, a little more expensive, but still we can rely on the results that we get. We can see, and because of that, I needed to make my domain to, let's say, 266 meters. We will have 6 different layers of soil, 1 to 6, and 1 embankment. We will have 2 feet of burial depth. We will have ramped embankment, as you can see. And here is actually the configuration of my soil domain. But what I have in the structure is consists of this. This is a foundation wall arch system, which I call it arch-only case. You can see the span is 54 feet, the rise is 20 feet, the thickness is 12 inches, and you can see the reinforcement details in cross-section of the whole arch here. This is a little dense, I understand, but as I told you, because there is not specified design codes for designing such cross-sections during seismic events, we need to do the existing ones, which, for example, I got it from reports in Pennsylvania Department of Transportation. On the bottom, you can see that there are a couple of properties that I'm using, the concrete properties and steel properties. We are seeing everything is the same. For the site properties, we have 2 sites. Some constant properties, which is Vs or shear wave velocity, rho or density, Poisson's ratio, friction angle, and C. These are constant for all the layers. But the thing that differs is their tau max or maximum shear strength, which comes from this equation, sigma V, which is the vertical stress, tangent phi plus C, which can be calculated. So basically, I will have 6 different embankments, and layer 6 have the same values. 6 different strength level that I need to take care of. But let's talk about, I told you one of my main concerns was to use fully nonlinear properties for my materials. The first material that I'm going to talk is the concrete. Modeling concrete in continuum domain, let's say like solid elements, has been always a struggle because of brittle behavior of concrete after getting cracked and exiting from a linear regime. And the good thing about LS-DYNA is that it has a wide range of material models that can model this type of behavior of concrete. I went with the concrete damage placesimal or MAG 273, which can allow us have some control over tensile damage on the top figure and compressive damage that we can see on the bottom. The compressive damage is kind of the same for most of the models. It's exponential after being cracked, the section being cracked. the behavior by increasing the strain would be exponential, which is the same as reality. But in the tensile damage, we can have three assumptions: being linear, being bilinear, or again being exponential. Which, based on the studies that have been done and based on the ideas of the developer of this model, the bilinear one will work the best for the matter of cyclic loading in reinforced concrete. For the steel part, we are having matte plastic kinematic or MAT 003, which is the very common method of simulating steel rebars in cyclic loading in different softwares like OpenSys. They do have the same implementation, and it is kind of elastic, kind of perfect plastic that we have seen. And we can both do it in kinematic hardening or isotopic hardening, which is a little more complicated and more actually exact in a matter of simulating the rebars. But being said, the most important thing or most important aspect of my modeling was the soil. So I needed to come up with a soil material that can mimic the behavior of my soil in reality, kind of the same or with a good accuracy. So we came up with a model which is called hysteretic soil or MAT 079. It is actually a nested surface model with up to 10 superposed layers. What does it mean? If you take a look at this figure, you will see that we have a bunch of elastic, perfectly plastic figures, elastic, perfectly plastic stress strain curves. By the way, we call this a strain curve as backbone. If we do them, if we simulate them in a parallel spring system, we can sum all of them up and generate this unified backbone curve, which can have up to 10 different slopes, and it would be a good representative of soil because it can be degraded. We can degrade the stiffness of the soil by increasing the shear strength, which is happening in real. And also, it has some different features that we are not very concerned about right now. But the most important thing was that. The thing is, when we're going to use this type of material in LS9, we need to define a backbone curve, which is consisting of a bunch of stress strain points. In this case, for this specific type of material, only 10 pair of data. So what is the best way to get a backbone curve? We can get it from different studies. For example, Darren Daly have done extensive study on different parts of US, for the California different parts, and he gives us some backbone curves. We can use that or other things as well. But we need to make sure that our backbone curves are calibrated enough that can both cover small strain and large strain regime of the soil. In order to do that, we needed to make sure that there is a hybrid way to actually mix these two regimes together, which led us to the study of Dr. Asimaki and Shi from Caltech. They actually provided a hybrid hyperbolic backbone curve that they took large strain backbone curve and a small strain backbone curve. They defined the different function from small strain to large strain. They combined all of them together. And then by doing an optimization algorithm, they found out the value that were constant there and they needed to recalculate actually. So the tau HH is the backbone curve that I'm going to use. But one of the limitations in the LS9 was that LS9 can only take 10 data points, as I told you, of the backbone curve. So I needed to come up with another optimization framework to only select 10 stress strain data points of tau HH to use it in my model. And those nodes needed to be calculated, picked, not randomly. They needed to have some criteria. For example, they needed to both take the smallest strain behavior, let's say the Gmax of the soil, and also the largest strain behavior, the soil strength. So I came up with that optimization framework and we're able to calculate that backbone curve that I'm going to use in my simulation. The last part of the just modeling was the input motion. The input motion, the focus of our study was actually the earthquake-prone area, something like Southern California. So we came up with a tidal spectra here that you can see. We got it from peer ground motion database. And after doing that, having that target, we found 6 ground motions that you can see the PGA, quick ground acceleration, PGV, and PGD of those motions actually. And we're going to use them in our simulation. But how? These simulations these motions actually are only surface recordings. And if we are going to use it in our analysis, we need to do some conversions. I mean that we need to have that we are having that surface recording, but we need the recording or input motion at the bottom of our soil column or soil domain or top of our rock where the motion starts initiated. This procedure in general is called deconvolution. As you can see, the deconvolution procedure flowchart I'm showing here. And this deconvolution can be done linearly or equivalent linear, which in the matter of being more precise and more exact, I went with the equivalent linear deconvolution. I use deep soil software, which is a very commonly used in these purposes, and got some soil properties like soil layering of my different 6 layers that I had, G over G max curves, which is the modulus reduction curves of the soil. Is a great indication of how the soil behaves when it gets nonlinear or when it stays linear. I will show you later on. And also the damping curve. I had these 3 aspects, use the deep soil, and got the equivalent linear deconvolution. Now, here it comes 2 things. My simulation consists of 2 major parts. One is the whole thing, the structure and the soil around it, which I will call it from now on the SSI case. And one time I'm going to only do the analysis, all the analysis only on the structure part without any soil to see the effect of soil on top of that and see how the seismic demands are different from that one. And as you can see, my soil domain is here. And the motion that I get from deconvolution is actually the one that's here. So that deconvolution motion that I extract is good in order to do the simulation for my SSI case. But when I'm going to do the same simulation for my arch case or arch only case, I need to have the motion at the foundation level, which will be here. In order to do that, and in order to find that motion, input motion for the arch only case, I needed to solve a one-dimensional propagation equation to only get the motion at that level. So now I will have both motions for my SSI case and also for my arch only case. So the numerical modeling, the overview was kind of this thing, and let's take a look at some. First things first is the model analysis of my structure. My structure, as you can see, has 2 main model fundamental frequencies. The first one happening at 2 Hz, and the second one is happening at around 5 Hz. That you can see the mode shapes as well. And on the right-hand side, we are going to compare some structural response spectrum and soil response spectrum. I'm going to give you some information about that. The soil surface that I'm mentioning here is a point here on top of my structure at the surface of the soil. And the arch crown that you're seeing in red would be I specified a node in the arch crown, so I will read those things. So soil surface is only for the soil one, and the arch crown would be a point into the arch at the very top. And you can see the SSI is for the case that I have all the soil and the structure together, and the arch only case is the only part that I will only have the structure. And I will have also the response spectrum of the input aspect. I have shown the fundamental frequencies of my structure with these vertical dashed lines that you can see. And one interesting thing that we can take a look at is that if you take a look at the black curve, we can see that the amplification of the black curve for the first one, second one, third one, and up to the last one are all happening around the first fundamental mode. So it seems that if we have only the arch structure only, it will the first mode will be actually controlling the deformation of our structure. But when we introduce the soil around that, we will see that the frequency content just gets, let's say, distributed among the first mode until the third mode. It doesn't reach the third mode, but it goes up to that. So it kind of shows that how the soil will affect our responses in this actually manner. And I'm having 6 figures. Each of these figures are for each of those motions that I showed you. The RSN 148, 187, 457, up to 1032, it should be. It's wrong. And this is it. The next thing that I'm going to show you is a little more important, which is the seismic structural demands and also the cross-section capacity to see if the demands that we have right now exceed this capacity that we have on the left side or not. Let's see. And in this case, we are considering three cases. The first case is only arch length, that we can see that the maximum structural demand. I'm showing the maximum vertical displacement here, and you'll see that when we excite everything, and they're all being run after the gravity analysis has been done. So all of them are the gravity analysis is taken care of. For the arch only case, we will see that the maximum displacement is happening kind of in the side of our arch, or in the 40 up to 60 degrees from the center of our arch. And in the middle or in the arch crown, we will see that we have the actually relatively minimum demand in the matter of displacement, vertical displacement. The same thing happens for the bending moment, that you're seeing that again from, let's say, around 40 degrees and here around 150 degrees, we are seeing the maximum demand in a matter of bending moment, and also the relative minimum one at the middle. And the same thing is happening for the thrust. What is thrust? Thrust is actually the axial force in the arch structure. We call them thrust. Once when we introduce the soil in our case and we have SSI, we will see here what happens. It kind of distributes the demand. At least for the first one, you'll see that for the maximum vertical displacement, we are seeing the distribution of the displacement, which the maximum is happening around the crown. So we are seeing that shift that comes from side to the ground, and it makes the sides a little less steep. The same thing is happening for the bending moment that you're seeing, but for the thrust, we are seeing such same behavior, but very smaller values rather than that. Because of existence of soil, some of those thrust force will be taken care of by the soil shear strength and all those interactions. In order to make sure that these conclusions are not only based on gravity, for example, because of the gravity and because the dead load of the soil, I took a look at the gravity-induced demand. It means that only by applying the soil load, soil dead load on top of my structure, I want to see how does it act. If you compare it with the higher case, upper case, we will see that it's kind of negligible in all of the cases. So we can see that all of these changes from arch-only case to SSI case is actually the result or direct result of the soil structure interaction effect. We talked about the structure, but what about the soil? We want to see if our soil gets failed, enters to failure regime, some failure rate is happening or not. In order to show that, I decided to go with von Mises stress distribution. I use this criteria because my model that I'm using is working based on the deviator stress tensor. And that deviator stress tensor can be converted kind of to the von Mises stress based on some formulation. And let's say if we compare our von Mises stress distribution with 2 times of our tau max, we can see that if it exceeds that amount, it will enter to the failure zone. If it's not, it doesn't. And as you can see, I only took 2 cases, 187 and 684, which are the 2 most extreme points. The 187 was the least demand on our structure, and 684 had the most demand on our structure. Just in the sake of time, so I didn't put all the 6 motions, the result of it. So as you can see from the fringe plot, we are barely seeing some points that gets to the red area. So we will see that we are still seeing some concentration of stresses around the arch, which makes sense. But it seems that the input motion that we are using is not actually making the soil to be fed. We are seeing nonlinearity because of those different slopes that we had in our numerical the material model, but we don't see any failure, which is not a very bad thing. But if you want to see the failure, we need to improve or amplify the amplitude of the motion. The other thing that is interesting is that if you take a look at the soil shear strain level at arch mid height level elevation, I mean here, what's in the far field, let's say we have a soil domain, we don't have this structure here, we only have the soil. The strain level would be from this value 0.018 up to 0.038, which if we take a look at the geoverge max curve, it will be around this point, which we can see that we are seeing, let's say 40% of nonlinearity. As I told you, the geoverge max curve is a good indicator of nonlinear soil, the behavior of soil in linear and nonlinear regime. And as we come from 1 to the 0, we enter from the linear regime to nonlinear regime. That is another observation that we have. We took two more things to discuss, to investigate. We wanted to see first the effect of soil nonlinearity on the response vector that we saw in the previous slide. And also, we wanted to see what happens if we make our soil surface embankment to be flat rather than just be round. In the first two figures on the top left side, and on the top side, we will see that effect of making the soil elastic or making the soil that we have, the soil model that we have, which is not. When we make it elastic in both cases, in both RSM 187 and 684, we are seeing that significant jump that we are seeing. And they will, or both of them are happening around the second mode of our structure. But when we increase the amplitude of motion, which is RSM 684, that jump would be even more crazy. And you see that it reaches to the SA of equal to 10 Gs. And this is actually an indication that we needed to use those type of nonlinear material, although we did not fail in soil, but using those nonlinear soil material caused those nonlinear soil happened to make our soil model more realistic. Let's say if I just had my soil material model as elastic, I would have some significant jumps and some significant amplification that was not necessary, and it does not happen in the real world, because real world, the real soil is not elastic. And the second thing that we took a look into was, as I told you, using the flat surface or round surface. When we make our surface, the embankment surface to be flat, we are increasing the soil level. Let me show you here. For example, here, you see, now it is round, but consider that these parts get filled up with soil. The soil will be, the structure will be even more confined. And that's the cause that you can see these dashed lines, which are for the flat surface, for all the responses, are getting de-amplified. And it can actually help us. And again, it's another indicator of the geometry of embankment, which matters in our simulation. And one of the most important things that people normally discuss when they're studying arch structure is the racking displacement. What is racking in arch structure? If we say that our structure is this, we say that point A is here, point B is here, which is the support of our arch structure. The racking would be actually the subtraction of these two points. And here we can see the maximum racking that's happening. And we can see that for the SSI case only, which are these square ones, they are all in the, let's say, the proximity of 5 millimeters. But when we use, for example, flat surface and elastic surface, we will see that the flat surface will increase the racking displacement in comparison to when we use only elastic soil and when we have the SSI case. And it is the same trend for both of these two cases that we have studied. And another thing is, I said that this soil structure interaction, this is actually for the SSI case. When we say that the racking is only 5 millimeters, if you remember, we had the shear strain here. These value of shear strain in the far field, by taking into account the height of our soil, are equal to around 1.5 millimeters. So it means that when we don't have any structure, the soil deformation or that shear displacement that we have in soil would be around 1.5 millimeter with these values of shear strain. But when we introduce the structure in it, we will see that it increases up to 5 millimeters, which is kind of significant. These were the things that we have done so far numerically, but the second phase of my study would be experiment and validating the thing that we have studied so far. And what we are going to do actually, we are going to use the UNR laminar soil box and shape table facility. All of you know that the facility is the largest biaxial laminar box in the US. It consists of 19 orthogonal steel frames. They are stayed in general on top of 408 elastomeric bearings in order to mimic the far field behavior, because it's, let's say, only 6 meters wide. And if it wants to mimic the far field, it needed to be higher if they did not use these elastomeric bearings. So they did that in order to just make the effect of the soil itself, the structure or the box itself, very limited and negligible. But what we're going to do, we are going to have a scaled version of our prototype of our arch structure inside our soil box. The scale would be 1/6. The prototype would be around 11 to 15 meter of span, but we're going to make it a scale of 1/6 of that. We are going to do the preliminary design based on the Ashland RFD for gravity loads and some seismic checks that is in NCHR 611 and Canadian Highway Bridge Design Codes, which they have some very, for example, in NCHR 611, they talk about the rectangular closed bottom culverts. They do the seismic analysis on that, and they gave some, let's say, simplified equation in order to calculate the seismic demand. But it's not exactly what our structure is, but it is the maximum thing that we have right now, according to the guidelines and design. And we're going to instrument our soil box by using strain gauges, accelerometer, and fiber optics in order to have a dense network of sensors in order to capture all the possible behavior of the soil. But there are some information about the box. A couple of years ago, they did the commissioning test and they have done some instrumentation. They shook the whole box with only 3 meters of soil, only the first 2 parts of the soil box. And they gave us some information that we used, and we took a look at that, which was on the left side. We are seeing that, and they shook with 1, 2, 3, 4, 5, 6 motions. They are scaled L-central earthquake motions, start from 11G, 0.11G, up to 0.69G. And if you take a look at the transfer function, which is calculated from the surface to bottom of the soil column, we are seeing that the peaks are shifting from higher frequency to lower frequency, which is the exact indication of making the soil nonlinear. When we make the soil nonlinear, it gets less stiff. Less stiffness means less frequency. And this was about the vertical wave propagation of the soil. We have taken a look at the central to middle. If you remember here, we have central, middle, and edge column of sensor. If we calculate, we have calculated central to middle transfer function and also central to the edge transfer function. You can take a look and you will see that until 14, let's say 15 hertz, we are seeing not very much oscillation, huge oscillation in matter of transfer function. So it means that the boundary effect of our box is not happening until that 15 hertz frequency. So we can say that in this area from right side and also the same thing on the left side, we can call it as an undisturbed area or undisturbed zone, where the reflection of the waves, which goes to the soil sides and gets back to the soil, is kind of negligible. The other scientific check that we have done, we only had the acceleration responses. So we used a method which was proposed by Zeman. We back calculated the stress strain curves based on the acceleration reports. And what we were able to get was that the maximum 2% shear strain was happening, which was consistent with what actually the commissioning report was telling us. And it was consistent, and it seems that all the things that we have is okay. All in all, it shows that if we put our structure in the middle of our box, we can expect to have the minimum wave reflection from the sides, and we can actually have a free field condition at the sides. Well, saying that, we have done it, and let's take a look at the conclusion that we had in this research. We developed a comprehensive numerical framework to assess seismic performance of very large structure, which we saw the pictures, under highway embankments. We addressed the lack of seismic design provisions in major codes like AASHTO, I told you. We took a look at the soil confinement that shifted peaks demand from sides to the crown of our arch. And also we saw that the soil nonlinearity broadens the structural response and enhances energy dissipation. We saw that those response spectra and we could conclude this. We saw that the racking information exceeds far-field strain prediction due to stiffness contrast. By introducing the soil into the structure, we saw those racking displacement were different. One was 5 millimeters, the other one was 1.5 millimeters. And also we saw that the geometry and stiffness assumptions strongly influence deformation. What about the future work? As I told you, we are going to, in the experiment phase, we are going to do shake table tests and verify our numerical models. So we will have a validated framework in order to have test different geometries only by simulations and get decent results. I'm going to do some expanded parametry studies on different arch geometries, cross-section geometries, different reinforcement, let's say details. Backfill depth and geometry, I will check different soil layering, and also I will use different type of motions, the higher amplitude motion, to see how does it affect the soil and the structure. And in general, it will all lead to develop a performance-based seismic design tool for various structure variables to support future updates to AASHTO, LRFP, and promote resilient, cost-effective infrastructure. And that's it. Thank you so much for attending. These are references. Happy if you have a question.
Thank you, Mustafa. Yeah, go ahead with any questions.
Not too many, is it plastic oriented?
Thank you very much for your presentation. I have a question about the non-linear characterization of the soil. Was Mason behavior or non-Mason behavior what you
Yeah. This type of materials, so material properties, MAT 79, is actually based on Mason behavior. And Mason behavior, for people who probably have less information, is a way that we define the dissipation of energy during cyclic loading. This is very initial version of MAT 79, which uses the Mason effect, and that can cause an over prediction of damping. There are other more complex version, or even in this version, I guess we can do some adjustment to make it non-Mason in order to make the damping, the material damping, more realistic. Yeah.
You can import the cures, damping cures using an option. I think,
Yeah,
exactly.
Yeah.
I have another question. Thank you very much for your response. You said you use deconvolution. I'm a little bit confused about that. What was the purpose of using deconvolution to obtain the ground motion that base?
Yeah, exactly. Because the pure motion that I got, they are actually the surface recordings. They're the records that are getting from accelerometers at the surface and everything. So I needed to get the top of the rock motion. So I needed to do that conversion, which is called deconvolution. So I equivalently using Gibson.
Do you have an opinion about deconvolution? Because I read some researchers saying about that deconvolution could be a little bit tricky because you are using transfer functions to obtain the ground motion, and sometimes it could not be reliable sometimes.
Yeah, that's a good point. I myself did not. The thing that I was able to do was instead of using the linear deconvolution, I used the equivalent linear, which were taking into account the layering, the nonlinear behavior by defining the geology max curves and the damping curves. So it still might have some uncertainties, but it was the best thing that I could do so far. But I will definitely take a look at that to see if I improve it or not.
Thank you very much.
Good question. Go back to slide 5. So that A6 for A6, that's for the steel reinforcement in that concrete, right?
Yeah.
How come you didn't use a A606 or A706 for your reinforcement?
Because I told you, I took this, details and specification from pretty constructed one from Pennsylvania Department of Transportation. They were using that. And I was just in the very early stages of just modeling this stuff. And as you saw, our demand do not make our structure to be nonlinear. One of the main reason is that dense spacing of the reinforcement. So if you change it to that, probably it would not have any very much difference with what we have right now. But this is the reason that I use that grade of steel.
Yeah, because I know like in the industry, like when I'm working, sometimes we'll call out different kinds of reform, typically use 706 for seismic design for it. So I was just curious.
Yeah. Yeah, as I told you, they are only doing it based on the gravity loads and those design criteria that are only for dead and live loads. They are not doing for seismic for these type of structures. Okay. Yeah.
I understand that you didn't see nonlinearity in the arc itself, but such a structure, do we expect to see nonlinear behavior in the arc? And if so, to what extent? I mean, that is actually quantified or modified down this definition or just structures?
Unfortunately for this type of structures, because they are kind of typical, like the steel profiles that we have typical structures of these types as well. So in most cases, they do not say that they allow something to get nonlinear because, as you know, they are mostly done and constructed in the hybrids. And they are kind of infrastructure, the very important ones. So if they enter to the failure zones, they could be problematic. But so far, I did not see anything about that.
Go ahead, Mohammed. Presentation. So in the next slides, we simulate the excitation side.
Where?
In this slide, we will simulate the excitation. This one.
Here?
Yeah. So you simulate the excitation, one for soil, one for structure. And I didn't get it why you use the two simulation because when soil is excited, it's related to the structure. Why did you couple this?
The reason is that we wanted to make a comparison apple to apple. Okay. So when we have an earthquake here, it's happening. We cannot use the same motion to the structure itself because the structure is laying on top of here. So we wanted to just see if the same excitation is happening and the structure gets the same motion in its level, how it performs. If we have the same input motion for both of them, then it would not be, I guess, apple to apple. You know what I mean? Because of that purpose, I needed to do it in two type of motions actually, and that was the reason.
I'm just curious, how did you model the interface between the arch and the soil?
They are based on, another thing is, these are not tight. We have defined contact elements, and those contact elements are working based on Coulomb friction. So we define some coefficients of the friction between soil and structure, and we define that, and they can just slip on top of each other.
Does it truly capture the interaction that is for nonlinear case? Soil, there has to be a gap opening, right?
There is gap opening. We did not have criteria in order to see if this gap opening and these slips are exactly the thing that's happening. But since they were, I showed you, the deformations are not starting, the failure wedges in soil, and we do not expect to have a lot of slips. So it seems that it's working very fair for now. But I don't know if we amplify the input motions, if they're still making sense, or we need to think something about that.
And then also, since you mentioned, if you go back to our ground motions, you see that there's significant scatter with respect to, especially the PG over PGV ratio.
Yeah.
So that actually will have, well, that's kind of an indication of the frequency contact, and maybe sometimes the existence of the pulse in the ground motion. So those will start becoming important when it comes to modeling those little nonlinearities that may take place.
Thank you.
We have time for one or two more questions, so we don't go too hard. I can do my question. So you said this bridge was from Pennsylvania. Are the structural details still relevant for seismic engineering? Like, is this a super useful case study? Like, would it have been more useful to pick a similar bridge in California where it's like, we already know there's gonna be a ton of earthquakes?
The thing is, they do not release the exact details and documentation of this type of structure because there are a couple of companies that they're constructing this type of structure. And because of that, we were so limited. And the only thing that I was able to get sketches of the structure and the detail of reinforcement was actually from the Pennsylvania. Definitely, it was not. It's not a good area because it's not very earthquake prone, but it was the least thing that we had. But after doing the experiments and making our numerical model to be validated, we can take a look at other geometries and other reinforced concretes.
Questions? I think we're good. Thank you so much for stopping.